So welcome back to the afternoon session. We decided we kick off the afternoon with a panel discussion. And what I'm going to do for the next 30 minutes, I would like to pick the brain of the HI, the human intelligence, represented by these five fine panelists here. And we want to talk a little bit about challenges and opportunities in the context of AI and physics. So before that, I'd like to introduce the elect set of panelists we have here. So I'm just going to start here and go all around. So we have here Maurizio Pierini, and I tell you who he is. So he's a senior scientist at CERN on the CMS experiments, did his PhD in particle physics at Sapienza di Roma, postdoc Lal, Wisconsin, and then since over 10 years, he's with CERN. And his research can be described as using machine learning to increase the sensitivity of finding new phenomena in the LHC data. Then next, this is not Balázs Kegel, who had to cancel last minute this morning due to a personal matter. But luckily, Gilles Louppe stepped up. He is from University of Liège, and he did his PhD in machine learning, also in Liège. And he worked a lot on the intersection of, as you saw this morning, machine learning, artificial intelligence, and applying this to physics. All right, then next we have Shirley Ho, leader of Cosmology X Data Science Group at Flatiron Center of Computational Astrophysics. She did her PhD in astrophysics at Princeton, and she's also associated, still with Princeton, with Berkeley Lab and with Carnegie Mellon. And as you saw in her talk, she tries to tackle challenging cosmology questions with machine learning, doing nothing less than understanding the universe entirely and fully. All right, then to my left, we have Danilo Rezende, Senior Staff Research Scientist at Google DeepMind. So he did his master actually in theoretical physics, École Polytechnique and Federal Institute of Theoretical Physics in Brazil. And then he switched to computational neuroscience here at this very EPFL. And his work can be described as, he works on generative models. Among other things, he is the co-creator of variational autoencoders, causal reasoning, and decision-making. And then finally, we have Lenka Zdeborová, researcher at CNRS in the Institute of Theoretical Physics, PhD in physics from Paris Sud and Charles University Prague. She was also a fellow at Los Alamos, and as you saw in her talk, she's trying to use statistical physics to solve problems in machine learning or to better explain why machine learning actually works. All right, so as you see, we have a very diverse set of panelists, and I want to thank them again to make themselves available. They have different backgrounds, come from different directions. But what unites them all, and all of us in the room here, is the enthusiasm for AI and physics. So before I start, I'd like to know from you if I were to ask you to put a label on you, right, to tell our audience a little bit where you stand on a scale from physics to AI. I know, where do you see yourself? Maybe starting with Shirley, Maurizio. Do you still consider yourself physicists?
I'm a desperate physicist.
All right.
Yes. I'm a physicist, but I'm reluctantly applying any methods I think it can be useful to solve physics problems.
All right. What about you, Gilles? Is physics just one domain of many, or is it special?
Yes, it's just one domain for me. My training is computer science. So I'm building the robots.
Okay. Let's go just round here.
There was some time ago a French newspaper who interviewed me and then called the paper Physico-Informatico-Mathematicienne or something like that. So I think I'm really everywhere.
Yeah, I cannot really say I'm a physicist, although that was my plan a few years ago. So I don't see physics as just one other area. It's the most fundamental of the science. So there's probably a lot you can learn from the machine learning side there. and probably used to accelerate research, machine learning to accelerate research there as well.
All right, thank you. So now the panelists outed themselves. I think it's only fair to ask the audience as well to give us an idea where you stand. So I'd like to make a little experiment now and just give us, an audible, make some noise if you stand either on the physics side or on the machine learning side. So let's start. Physicists, make some noise. Where are you? Physicists, woo, woo, woo. Clap if you can, clap. Okay, let's try to measure that. Okay, now where are the AI folks? Noise. All right. Is there a third group? Is there other? Neither nor. Yes. All right, one. No. No, yeah, we want to keep this as diverse as possible, so perfect. So it's an excellent audience. Thank you very much for taking part in that. So maybe now follow-up questions on the labeling that I gave to you. So another question is what really excites the people here on the panel? So what drives you? What keeps you up at night? Is it the physics questions? Is it the puzzles of the universe? Or is it the exciting prospect of redesigning, reshaping AI and applying it to some puzzles? Who wants to give it a shot? I mean, is it according to, you're driven by physics still?
You say what doesn't make me sleep at night. So what doesn't make me sleep at night is that we produce at the LHC 40 million collisions per second, and we store 1,000. And we store 1,000 based on the fact that we decided a priori what we're interested to. So now that we ran out of things that we knew we were supposed to find, we're basically looking for something in a dark room, and we might be looking in that corner there, and the thing is sitting here, and we're just not even saving the data. So what doesn't make me sleep at night is this, and this is what motivated me to try to approach deep learning, particularly anomaly detection, as a way to have an insurance policy. So I'll keep doing what I'm doing, but meanwhile, with these new tools, I can try to design another way to deal with the data in real time that is looking behind my back. And this is, I think, is the most exciting thing that I can do. But of course, there are many other things that can be done. But if I have to single out one, it would be this one.
Anyone who wants to?
What keeps me up at night is the possibility and possibly the hype, maybe the potential that these new methods that I kind of look at deep learning as sort of like a new Newton's method or new numerical method that can solve a lot of different problems. But the one problem I really want to solve is to take, these $1 billion worth of, data about space, about the universe, and turn it into an insight that would not have been possible without these new methods, and a lot more accurately. So this probably applies to not just cosmological data set, but also other data sets.
All right, thank you. I mean, if you want to, please.
Yeah, maybe the thing that drives me, the dream that drives me, it would be to replicate to some extent the same astounding success of physics in modeling the world, but in an automated way. So how can we build a machine that discovers Newton's laws and then figure out that it cannot explain black body radiation, and then figures out quantum mechanics, and then quantum field theory, and then string theory? How can we automate that? So that's the thing I would like to build.
Yeah, my motivation is not maybe that concrete. It's really the little girl curiosity about everything, and kind of the magic of being able to be at the boundary of what humanity knows and what humanity doesn't know, and pushing little by little this boundary forward the best I can. So I guess that's kind of the driving force. And
I'm going to make it full.
Okay, so one of my motivations is really just to advance human knowledge and to understand how we actually build science. So how do we build scientific knowledge? And I think when you look at the scientific methods, there are many parts that could be automated or in which machine learning could be really helpful.
Maurizio, a question for you. What do you see is the role of CERN in this? Have you converted our Director General Fabiola to the AI world?
I'm working on that. I think that we are clearly not doing fully our homework. We should really step up and do more. It is still too much of a corner of what is done. For those who are not familiar, our community in general, traditionally, it's very, very conservative on its practice. And before you establish something new as mainstream, it takes years. And we started this with a few people here sitting with me and a few people in the audience, 5-6 years ago. And now we start seeing things moving. But it's gonna take time. We're gonna have the next round of the LHC in the terms of the economy of the classic way of doing stuff is gonna be marginal. It's not gonna be like before. We're gonna double the data set, we'll improve precision by square root of 2, okay. But it's really an opportunity to commission this with real things. And at that point, I think that the more we push, the more the experiments push in this direction, the more CERN will acknowledge the importance of this and the more it will invest there. So my ultimate dream is that eventually we recognize that the traditional approach to high energy physics as something vertical, where from the electronics to the statistical method used on the last step of the analysis, everything is done by particle physicists, should be abandoned. And we go more in a horizontal kind of thing, where we have computer scientists, data scientists, engineers, physicists working together, committed the same way. It doesn't mean that CERN needs to be become a port for people to come, have a postdocs, and then go to work at Google. You need people to be focused and committed, but it would be nice to have the tools to incorporate these different skills inside a career path that allow these people to commit long term. We currently don't have that. And this is where we're insisting.
Okay, let me take this one step further. So with AGI, we are not yet there. If you try to assign an IQ to Google AI or Siri, you find they have IQ lower than a 6-year-old. On the other hand, we have narrow AI, which is superhuman. Can play Atari games or do facial recognition better than humans. So the gap between these is the prospect will narrow. So what does that mean for physicists? So Gilles, what do you think? Does Shirley have to worry about her job? Will her job be taken over by an automatic physicist in the future?
No, not really. Not in the near future. I think we are nowhere close having AGI.
So if you look, for example, at the scientific method, right? So you have the hypothesis generation, and then you have the experiment design, you have the data collection, and then you have the inference loop. Which is the hardest to automate? I mean, we heard already from you this morning. Inference is solved, it's automized. Which part is the next?
I think one of the main problems is to build a model. So in my talks this morning, for example, I start with a simulator. This is given to me, but this simulator is the result of decades of research from thousands of researchers, and that's not something we manage to learn from data yet.
Can I respond quickly? Yeah. Does that mean that we'll become the department of not physics or astrophysics? It will be the department of training data generation.
I mean, we have generative models, right? Can't generative models produce theories, non-trivial, relevant theories like our theory friends can, I mean, what's their method of, I mean, we have a theorist here, right? What's their method of coming up with models? Not a particle theorist, but like the models are, you know, extensions of the standard model, extensions of the standard model of cosmology.
Yeah, maybe one way to put it is that where AI is still far away is kind of in what questions should we ask, right? Because the way I see AI is like if we give it a specific goal, specific performance function, loss function, then it can, and you know, parameters it can twinkle. It's like good at setting those parameters to the right thing. But I don't see anything that would kind of hint towards the part of our intelligence that is, this is the subject that I study. How do I go about it? What does understanding mean? What is science? What is satisfying us? What is this thing that we are looking for? This is really something that so far we humans are deciding, and I don't see this being formalized at all, actually, so far. So one day, of course, maybe, but I mean, we have the biological proof that general intelligence, that you know, our brain exists. So technologically, there is no reason why we should not be able to do better. But I'm not seeing that happening in this like wave of machine learning revolution. Maybe in 100 years. I don't know.
Okay, good. I think we seem to agree. We want to keep the human in the loop. Yeah, that's. I'm very happy because in the end we're having fun doing this. But maybe let's talk about this for a moment, right? I mean, it's hard enough for us humans to collaborate in big collaborations like in cosmology and particle experiment. Now we add a new community of data scientists who speak a different language, have different incentives, different goals maybe. So how do you maybe tell people in the audience, how do you make it work, this collaboration? How do you make it efficient and worthwhile for both communities? Do you want to? Who wants to give a shot? I mean, I assume you're all working somewhat with both physicists, right? And machine learning AI folks. What's the secret?
Just as a short comment, I think having workshops and a conference like this where both fields collide is a very good way of forming collaborations and sharing ideas in both directions. So I think that's very good. And we also do see in both physics journals and machine learning journals and conferences more cross publications, which is very good. So, and if you just do some basic statistics on NeurIPS, iClear, and physical review letters, etc., you see a growth in papers both ways, which is very nice to see.
Maybe one way to put it, I mean, I kind of see, you know, this question is about multidisciplinarity. I kind of see like two different kinds of multidisciplinarity. One is driven by the problem, like a big problem, for instance, I don't know, climate change. I mean, we clearly need many people from many different disciplines to tackle that problem. And in companies, we often have problems of this kind, where it's clear that you need people with different expertise to advance in the problem. And then there is the kind of multidisciplinarity, where kind of one discipline, in my case physics, tries to look at questions that kind of belong to another discipline. And a priori you would think this is maybe not even needed. I mean, what is the use for that? Is that just like that physicists have big ego, whatever? So for me, the value of the second kind of interdisciplinarity is that it's only once you kind of go to a different field that it makes you understand what are the intrinsic assumptions of your field that you don't really question very often, that are kind of everybody agrees that's the way we do it, right? In physics, we start with models and that's the way we proceed. But then I go to talk to my computer scientist friend and the very idea of starting with the model is completely alien to them. And the discussion about why is it a good idea and what are the questions that you kind of can answer this way and which questions should you actually ask? I mean, this is really interesting when you actually try to make people from different fields talk about one subject that a priori maybe didn't need that discussion.
Right, so there is probably even much more to gain from this. I mean, we're just starting with interdisciplinary work, right? We haven't fully explored what could be gained if we really fully take advantage of mixing and matching in the right way all the disciplines. So here, I'm coming back to AI now. Could AI help us, you know, to figure out what are the interesting regions, the opportunities where we can advance research. You know, I mean, humans have a limited capacity, limited memory. We cannot read 100 machine learning papers per day, which is the current rate. I just learned yesterday here. Feynman was the last who fully understood physics. Now it's not even possible to understand a subfield of physics. You know, we need help. Can AI help us to do better research in this sense? Turning to the other side. It's, you know.
I mean, yes, I suppose you could try to build something like recommender systems to pass through all this deluge of archive papers, and then they could align with your own interest as a researcher. I think, for example, tools like Archive Sanity that I use almost daily, it helps you a lot in just finding papers that are interesting to you without having to read the 50 papers that come out on the same morning.
It sounds like it's needed, right? There's no way around it. Yep.
I want to comment. Recently, there has been an experiment at the iClear conference where for the area chairs have access to a map, a two-dimensional map of how each iClear publication under review sits on a bunch of previous publications in the previous years, and that's, for example, is one tiny little tool that's very helpful to situate each paper that you are reviewing in a bigger picture. And I could imagine that this kind of tool to be more broadly useful as well, to be able to literally navigate through the papers.
So we talked a lot about how AI can help physics, and then Lenka told us how physics can help machine learning, right? And I don't want to repeat your beautiful talk now, because I think you made it very clear, and you have a very nice path to move in the future, and I'm looking forward to the new results. But maybe is there anything else where physics can help machine learning? I mean, you're a physicist. You have your background in computational neuroscience, and a lot of machine learning is built on this. Where do you see the future of some people talk about smart neurons versus just a dumb neuron who just sums up physics. What do you see? Is there any development in the future we can expect?
Right. So what I think about this is that we need better tools to integrate domain knowledge and more general structural knowledge about the domain into machine learning. So until very recently, where people are not thinking about the graph nets, for example, what was the domain knowledge that we put into machine learning is a convnet, translational invariance, that's it. And or if you have sequential data, use the recurrent network. This is the kind of domain knowledge that the people are building to these models. Of course, in a very niche applications, people are thinking about other domain knowledge, but and then there's a GraphNet. So GraphNet is a much more general data structure that has as particular cases RNNs and the convnets, and it found a very natural way in, for example, fundamental physics, and also in molecular dynamics, where it can have things that are very well described by a small number of interactions, for example. So there's a good match there. But I think we need a lot more tools in this direction. How can we find the right compromise between building up our knowledge and learning?
Maybe before speculating about how in future physics is helping machine learning, let's just be clear that physics already helped machine learning immensely in the past. Why do you think we call the restricted Boltzmann machine the Boltzmann machine? Or Boltzmann didn't know about machine learning. Why, the wide class of variational mean field algorithms? I mean, I learned about that in Feynman's books, and that's a huge area that is applied in many practical applications in data science. Or the very idea of simulated annealing. This paper has, I don't know how many tens of thousands citations. So we should just not shy away from this and keep doing that. And then this question will naturally answer. Of course, physics is a very universal kind of science, so it helps many other sisters sciences.
All right, thanks a lot. So we're reaching the end of the panel, and it's just about the right time to see if there's any burning question from the audience, and I just saw one. Yes, we need to bring your microphone. Hang on. Could you read?
I have a question about what do you think about the future of quantum machine learning? We use quantum computers to do machine learning.
Who wants to take this one? Quantum, Jean, you want
I mean, for me, there are, that's another way in which physics is kind of helping machine learning and other domains is the hardware development, right? There are many companies and researchers working on specific hardware for specific tasks. And for me, currently, as far as I know, quantum machine learning in, say, 10 years is falling into that class of a hardware that will be really, really good for some very specific tasks. Like, we don't really know yet today which ones, but say in 5-10 years, this I see is foreseeable that we will know. So then I'm imagining that in the computer where we have the CPU and the GPU today, we will also have a QPU, and we will also have maybe OPU, like optical processing unit, quantum processing unit, right? Graphical computing, and who knows what else. So I think that's a pretty realistic kind of idea about how quantum computing will actually be part of computing in some near future.
Okay, we take one more. Yes.
So my question is just about theoretical physics, and you kind of mentioned this aspect about maybe it's 100 years before we can sort of ask the right questions and so on and so forth. I was wondering, just currently right now, what is the biggest bottleneck from being able to abstract away these like very compressed equations or deep understandings that we get in, like, for example, special relativity or even Newtonian mechanics? So one could argue that, for example, a lot of this insight is somehow not just pattern recognition, or it's some sort of additional leap of creativity required. And I'm just wondering, currently today, what is the biggest challenge?
So I don't know if you saw my talk earlier, but we combined graphical network and symbolic regression, and we were able to look at a bunch of data sets and derive the Newton's law. So that wasn't completely crazy. The bottleneck was someone wants to do it. And this was actually done earlier in 2009 with like simple layer of neural net plus symbolic regression. So it was done in that sense. The other thing I think that will be hard to do is to find a new physical law that wasn't expected in some ways. So you can probably like throw it into the symbolic regression into like one of the possibilities to choose that you can search for. But you need to simulate at some level. You need to have a bunch of training sets. So where did that model building, I think Maurizio was talking about earlier, that came from?
Okay, so I will close with one last question for all the panelists. So what is the hot stuff you're working on? In other words, what we will talk about at AI and Physics in 2021 here in AMLD. If you want, you can single out just one thing. If you don't feel certain about the next year, you can also do it for 2025 if you want.
I'll just go because I'm really excited about this project. I don't know if people know about merging black holes, these things of gravitational waves and all this stuff you just recently heard from LIGO, and it will be with Lisa. And the numerical relativity simulations are extremely hard to do. It took 40 years before people can put a stationary black hole and not disappear. So right now, a team of our colleagues were actually working together to basically use deep learning to do the simulations of merging black holes. We'll see how it goes. So right now we have like 1D stuff maybe working. But getting to 3D and getting to really crazy corner cases, that will be very interesting. And I thought, this is a really hard problem to solve, and be cool to solve general relativity that way.
Okay. One of my topic of research that I think I will develop is how do you get the most, how can you choose the most of your simulator, for example, and in particular to do causal inference?
So one thing we're working since 1 year, it's a tool that allows to automatically turn ideally every model that you come out with into an electronic circuit that you can emulate on FPGA or eventually print it on ASIC through a full automatic conversion process that goes from Python to C++, from C++ to the FPGA firmware. And the idea is to use this to having the network completely on chip, such that you don't have to do back and forth with memory and be able to do inference at within a microsecond, which is actually less than a microsecond, hundreds of nanoseconds, to ideally have, I don't know when, 2030, our full level 1 trigger running on machine learning algorithms.
Yeah, I think this question that I was posing earlier about why the overparameterization is important and how to explain that dynamically, I think that's a one that is quite within reach of the time scale that you were saying. So I think we will be discussing more about that for sure.
Thank you. One thing I'm excited now, and I think a lot of other people are, is that most of machine learning has been up to recent years has been concerned mostly about passive data. So someone give you a data set and you collect a data set and then you do a bunch of regression there. But we are I think I'm very excited about completing the loop of collecting data. So now we're building agents that walk around in an environment and collect the data and train a model of the data as they are collecting. And then the model informs how the data should be collected as a consequence. And there's a lot more to develop in this direction, but I think that that is moving away from passive data to active data is a very important step to building robust models, actually addressing causality in learned generative models and things like that. So I think it's a very exciting direction, and there will be a lot of papers the next couple of years.
Okay, so next year, 200 papers per day. Yeah? Okay. All right, so with that, I think we close, and I would like to thank all the panelists.